Hello, Math 200 students. This is my second attempt to make a 4.2 and 4.3 video. I made these videos already, and I think I had my headphones plugged into my computer because the sound didn't work at all, and I think that was why. So, take two. Chapter 4 is about the discrete probability distributions. If you remember discrete, the word means that it skips things in counting. So 1, 2, 3, 4. I'm skipping numbers when I'm counting like that. There's an infinite amount of numbers between 1 and 2 and 2 and 3 that I'm skipping over. So discrete distributions count discretely like that. Sections 4.2 and 4.3 are about three common discrete distributions: the binomial, geometric, and this word here is Poisson. It's, kind of French. You got to say it with a little French accent. Poisson distributions. So I want to explain to you the difference between those right off the bat. And I'm going to do that with the free throw analogy. Okay. The binomial distribution would say the number of free throws made out of 10 shots or 10 attempts. Okay. The geometric would say the number of free throws attempted until the first shot is made. Okay. So, and then the Poisson would say the number of free throws made in 10 minutes. So there's the difference between these three. If you can keep that analogy straight in your head, that should give you the framework, the categories for these three different types of discrete probability distributions. So binomial. If I shoot 10 shots, the binomial distribution is going to tell me the probability of making X number of shots, whether X is 5 shots or 8 shots or 1 shot or 0 shots. Okay, but it's out of however many, out of 10 or out of 20 or something like that. Poisson is very similar. Poisson is, again, how many shots I make, but not out of a certain number of attempts, but in a certain amount of time. So how many shots do I make in 10 minutes? Okay. And then geometric is different than those. It's more by itself than those two. It's how many shots does it take until I make the first one? Okay. So it might take me, I might make the first one, or it might take me 10 shots before I finally make one. And that's what the geometric distribution tells me, the probability of what's the probability that it takes me 5 shots before I make the first one. All right, so let's go on to talk more about the binomial distribution in 4.2. There are many probability experiments for which results of each trial can be reduced to 2 outcomes. Okay, here it is: success and failure. That's a big time component of what a binomial experiment is about. For instance, when a basketball player attempts a free throw, he or she makes the basket or does not make the basket. Probability experiments such as these are called binomial experiments. Here's the definition. It's binomial if it satisfies these conditions. The experiment has a fixed number of trials where each trial is independent of the other trials. Okay, so your second shot can't be affected by your first shot, and so on and so forth. All right, there are only 2 possible outcomes of interest for each trial, and they can be classified as success or failure. Do not think of the words success and failure in the normal everyday usage of those words. We're not defining them that way. So if you're trying to figure out, well, how many wrecks occurred at this intersection out of 1 million cars passing by, you would define a wreck as a quote-unquote success, and that doesn't mean you're some demented person that is thinking, oh, yay, another wreck. It just means you're counting it that way for the purpose of the mathematical formula in order to calculate the probability that that number of wrecks has or would occur. Okay, so again, don't think of successes and failure as our normal usage of those words. It's just how you define it, however you want to define it in that experiment. All right, number 3, the probability of success is the same for each trial. That's important too. All right, it has to be the same probability of success each time. We'll talk about that later. And the random variable x counts the number of successful trials. So here's the symbols for binomial experiments. N is the number of trials. P is the probability of success in a single trial. Q is the probability of failure in a single trial, so that's the complement of P. It's 1 minus P. And X is the random variable that represents the account of the number of successes in N trials. So let's take my analogy of the 10 free throws. If I'm counting, let's say I'm a 60% free throw shooter. That means I make 60% of my free throws. Every time I shoot a free throw, I've got a 60% chance of making it. And I want to count, what's the probability that I make 8 free throws? Okay, so N would be 10 because I'm talking about out of 10. P would be 0.6, 60% chance of making the shot each time. Q is going to be 0.4, which is the probability of not making the shot, which is the complement of P. So 40% chance of missing each shot. And X is going to be 8. What's the probability that I make 8 shots? Okay. So here's another example. Example of binomial experiment. From a standard deck of cards, you pick a card, note whether it is a club or not, and replace the card. You repeat the experiment 5 times, so N equals 5. The outcomes of each trial can be classified into 2 categories. S for success would be defined as selecting a club, and F would be not selecting a club, selecting any other card besides a club. All right, so the probability of success then is the probability of selecting a club. There's 13 clubs, and there's 52 cards in total, so 13 out of 52, which is the same thing as 1 out of 4. So probability of success is 1/4. Probability of failure, Q, would be 1 minus that, which would be 3/4. All right, and the random variable X represents the number of clubs you select. So it could be 0 clubs, it could be 1 club, 2, 3, 4, or all the way to 5 clubs. So for instance, if X equals 2, then exactly 2 of the 5 cards are clubs and the other 3 are not clubs. So here's an example of that over here where you've got 2 cards in the 5 that are clubs and the other 3 are not. Okay. Moving to the next page. Another example. Determine whether the experiment is binomial. If it is, specify the values of N, P, and Q and list the possible values of the random variable X. If it is not, explain why. Number 1, a certain surgical procedure has an 85% chance of success. A doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. So is that binomial? The question is, does it satisfy the conditions we talked about earlier? Can we define it as a binomial outcome, which we can say this is failure and this is success? And it is, yes. Is the probability the same on each trial? Yes, it's 85% chance on each trial. This is a binomial experiment. X is going to count the number of successes. N, what is N? The number of trials. N is 8. What is P? The probability of success on each trial. P is 0.85. What is Q? What is the probability of failure on each trial? It would be 1 minus 0.85, which will be 0.15, 15%. Okay, that does it for that one. All right, next one. A jar contains 5 red marbles, 9 blue marbles, 6 green marbles. You should randomly select 3 marbles from the jar without replacement. The random variable represents the number of red marbles. So this is almost a binomial experiment. The reason it's not is because these words in italics here, without replacement. That means that whatever your probability of selecting a red marble on the first choice was, because you didn't put whatever that marble was back, the probability of getting a red marble on the second choice is going to be different than it was on the first one. So if you get a red marble first, the probability of getting a red marble next is going to be less than it was the first time. If you pick anything but a red marble the first time, then the probability of getting a red marble on the second one is going to be greater than it was the first time. So if this had said with replacement, so that your probability of getting a red marble is exactly the same thing every time you pick one, then it would have been binomial. All right, moving to the next page. There are several ways to find the probability of X successes in N trials of a binomial experiment. One way is to use a tree diagram and the multiplication rule. Another way is to use the binomial probability formula. I'm going to show you a couple of ways, and the last way I show you will be the easiest way, and I think it's probably the one you're going to use the most, but let's work our way up to that. In a binomial experiment, the probability of exactly X successes in N trials is this. So, the probability of X successes in N trials is NCX. We also could call that N choose X or N combination X times P to the X times Q to the N minus X. And that works itself out to this because NCX is this right here. All right. Rotator cuff surgery has a 90% chance of success. The surgery is performed on 3 patients. Find the probability of the surgery being successful on exactly 2 patients. So let's pretend we have these 3 patients. We want exactly 2 of them to be successful to calculate this probability. So let's say the first one is successful. What's the probability that happens? It's 0.9. Let's say the second one is successful. The probability that happens is also 0.9. Then the third one would not be successful. The probability that is 0.1. But that's not the only way it could happen. All right, we get that number. So another way it could happen is we could have the first one be successful, the second one not be successful, and the third one be successful. That's going to give me another one. Another way we could have it is the first one could be not successful, the second one could be successful, and the third one could be successful. That's another way it could happen. All right, so add all those up and you get the total probability that you have exactly 2 successes. Well, that is exactly what this formula right here does, okay? 3 choose 2 times 0.9 to the second times 0.1 to the first. And that's the formula. It's NCR times P to the R times Q to the N minus R. That's exactly what we just did. Okay, so notice that that's what's happening here. This is 0.9 to the second and 0.1 to the first on each one of these. 0.9 to the second, 0.9 to the second, 0.1 to the first, 0.1 to the first on each one of these. And the 3C2 is what makes it where it doesn't matter where the 0.9s and the 0.1s occur. It's just as long as there's 2 of the 0.9s and 1 of the 0.1s. All right, so let me show you how to do that in your calculator. We can say 3, then hit math, click over to probability. The third option is the NCR option. So 3C2 or 3 choose 2, click to the right to get out of that. Then 0.9 to the second and 0.1 to the first. These 2 numbers right here will always add up to the number of trials. So 3 trials, so these 2 numbers will add up to that. This is the number of successes, this is the number of failures. So the probability that I have exactly 2 successes is 0.243. Now let me show you probably the best, maybe easiest way to do it. You see this right here, this word right here, DISTR in blue above the VARS button? It's short for distributions. So this menu here gives me lots of different distributions in my calculator. We're going to talk about the normal distributions later, but click down, go down for a while, and you'll eventually get to binomial. So we have the Binomial Pdf and the Binomial Cdf. I'll tell you more about that in a minute. We're going to choose Binomial Pdf. Okay, how many trials are we talking about? We're talking about 3 trials. P is the probability of success on a single trial. We said that was 0.9. The X value, we're talking about having exactly 2 successes, so that's X value would be 2 then. And then we just go down here and click paste and hit enter again, and it gives us the same exact answer, and that's probably a lot easier to do. Okay, let's keep on going. By listing the possible values of X with the corresponding probabilities, you can construct a binomial probability distribution. All right, so next example. in a survey, U.S. adults were asked to identify what devices they use to access social media. The results are shown in the figure. 7 adults who participated in the survey are randomly selected and asked whether they use a cell phone to access social media. Construct a binomial probability distribution for the number of adults who respond yes. Okay, so first of all, what is the thing about? What is the success and failure that's being asked about in this problem? Well, it says they are asked whether or not they use a cell phone to access social media. So we're going to define success as them saying yes. I do use a cell phone. So we're going to say using a cell phone is success, and I don't use a cell phone is failure. So what is N? What is the number of trials? Well, it's given right here. 7 adults are surveyed. So 7 is the N. That's the number of trials. What's the probability of quote-unquote success? The probability that they use a cell phone. You can see it from the graphic here. It's 46% or 0.46. What is the probability that they don't use a cell phone then? Or Q in this case. 0.54. 1 minus 0.46. So if we're going to construct the entire binomial probability distribution, then we're going to have to figure out the probability of every possibility. What are the possibilities? Out of those 7 adults, it could be none of them use a cell phone. It could be 1 of them does, or 2 of them, or 3 of them, all the way up to all 7 of them use a cell phone. I've got to figure out the probability of each of those possibilities. So I'm going to go to my calculator. I'm going to say 7. Well, actually, the easier way, we've already said, is to do the Binomial Pdf. So I'm going to go second distributions. If you just hit the up button instead of the down button, I think it probably gets you there a little quicker to Binomial Pdf. The number of trials in this case is 7. The probability of success P is 0.54. Or was it? I know, maybe I got that wrong backwards. It was 0.46, wasn't it? Probability of success is 0.46. 0.46. And the X value, let me start with 0. And so my first probability would be 0.013, or about 1.3%. Now, what I can do to make this easy on myself is I can go up here and click enter on what I just typed in, and all I have to do is change the 0 to a 1. So now it's going to give me the probability that I have 1 person, and that's about 0.07, almost 0.08, so about 8%. All right, do it again. Go up there and highlight that and hit enter, and just change the 1 to a 2. And that's going to get it a lot quicker for you. 20% chance there. So you can see here that they go all the way, they do all of them all the way to 7. They have all these different probabilities for the entire range of possibilities from 0 to 7. That's the entire binomial probability distribution for that example. Notice that, go back and notice that all those numbers are between 0 and 1, and that they all add up. If you add them all up, they add up to 1. Okay. This example is showing us how to use our calculator, but we've already done that, so we will skip that example. We'll do example 5 here. A survey of U.S. adults found that 62% of women believe that there is a link between playing violent video games and teens exhibiting violent behavior. You randomly select 4 U.S. women and ask them whether they believe that there is a link between playing violent video games and teens exhibiting violent behavior. Find the probability that 1, exactly 2 of them respond yes, 2, at least 2 of them respond yes, and 3, fewer than 2 of them respond yes. All right, so let me write some of that information down here. What are we talking about? We're talking about 62%, 4 of them are selected. Okay. So 4 women, P is 0.62, so the first one asked me, what's the probability that exactly 2, probably that X equals 2, that exactly 2 of those women would say yes, they do think that violent video games has a link to violent behavior. So we're going to go second distributions. We're going to go to Binomial Pdf. And we're going to say the number of trials is 4. P is 0.62. And the X value is 2. And it gives me 0.333, or about 33%. All right, the second one, what does that ask me? That one asks me, what's the probability that at least 2 of them respond yes? Probability in this case is that X is greater than or equal to 2. So at least 2 means it could be, that's the probability of 2 or 3 or 4. Since we're asking 4 people, probability that it's at least 2 people could be that's the probability that it's 2, or the probability that it's 3, or the probability that it's 4, all added together. So I can go up here to my calculator and put that in. I've already got the 2 in there. Let me do the same thing and put the make it the 2 be a 3. And do the same thing again and make the 3 be a 4. And that's going to be, so I got 0.362 and 0.148. That's 0.362, 0.148, and I've also got 0.333 that I already calculated in the previous example. So add all those 3 together and you get 0.843. All right, and the third one says, what is the probability that fewer than 2 of those women said that there is a link? So the probability that X is less than 2 this time. So that's going to be the probability that none of them do, plus the probability that one of them does. So X being less than 2, the possibilities are 0 and 1. So I'm going to go to my calculator. I'm going to do the same thing I did before, except I'm going to change X to a 0 and a 1. So 0 and 1. And I'm going to add those 2 together. I'm going to add the 0.0208 with the 0.136 to get the final answer of 0.157, basically. 0.157. Okay, now let me show you another easier way to do problems like that. When it asks you, what is the probability that exactly this many people or this many objects or whatever, when it's an exact number, then use Binomial Pdf. But when it's a range of numbers, like what's the probability that it's at least 2? Or what's the probability that it's less than 2? There's actually another way to do that that's a little quicker. So Binomial Cdf is going to be applied here. So if I go to second distributions, and instead of doing Binomial Pdf, I can go Binomial Cdf. All right, this number of trials is still 4. The p-value is still 0.62. Let's say this is a cumulative distribution function. So whatever I put in for X, it's going to tell me the probability that it is at most that number, that everything leading up to that number is going to add all the probabilities up all the way up to the number you put in. So let's say if I put in 1, then it's going to tell me the probability that it's either 0 or 1. It's going to add those up and tell me the answer already. So notice the probability is the same thing I got before. When I put in the 0 and the 1 and added them together, it gives me the same thing in 1 step here, instead of like 3 or 4 steps. Okay. What if I wanted to know, so let me go here and say what we can do. We can just say Binomial Cdf, and we put in 4 and 0.62, and we can put in 1 here. So the probability that x is less than 2, I need to put 1 for my x in my CDF, and it'll tell me the answer. Because it tells me, again, the cumulative probabilities all added up to, all the way up to and including the number you put in right there. So I didn't need to put in 2 because I didn't want it to include 2. I wanted it to be less than 2. What about this one? Can you think of a way to do number 2 that way? What's the probability that x is greater than or equal to 2? How can I use Binomial CDF? If I do Binomial CDF, if I want it to be greater than or equal to 2, I can do Binomial CDF with 4.62, and I can put in 1, and then I can subtract that from 1. Because this is going to be, this right here is going to give me 0 and 1. And so 1 minus that is going to give me, 1 minus that whole thing is going to give me everything but that. So what's everything but that? 2, 3, and 4. So it's the complement there. So anytime it's, you want to know something that's, when x, probably the x is less than a number, you can use Binomial CDF and put in 1 less than that number. Or if it's less than or equal to that number, then use that number. If you want to calculate the probability that x is greater than a number or greater than or equal to a number, you're going to have to say 1 minus the Binomial CDF. Let me show you. So with the probability that x is greater than or equal to 2, I'm going to say 1 minus Binomial CDF when x is 1. And that gives me the exact same answer I got before when I added up the 2, the 3, and the 4. 0.843. That's probably a little confusing to you, but I hope you can get a hold of that because it'll make things more efficient and faster for you to make your calculations. Okay. Let me read this. You can use technology to check your answers. For instance, the TI-84 Plus screen at the left shows how to check parts 1 and 3 for example 5. Note that the second entry uses the Binomial CDF feature. A cumulative distribution function computes the probability of x or fewer successes by adding the areas for the given x value and all of those to its left. Same thing I said before. Finding binomial probabilities for the binomial probability formula can be a tedious process. To make this process easier, you can use a binomial probability table. I would recommend not. So they're showing you right here how to use a table, like in a statistics book. Like there are tables in the back of the statistics book that you can use to calculate binomial probabilities or other probabilities. I would say don't ever use that. I wouldn't recommend it. You're welcome to do it if you want to do it, but in my opinion, we have the technology to do that without having to look at tables like we used to have to do when I was a student. We used to have to go to the back of the book, find the appropriate table, and find the appropriate thing, column and row, to find the probabilities that we needed. But with the calculator, it just makes this much easier, and you're going to have a calculator with you more often than you're going to have a statistics book with you. So I would recommend using the calculator instead of using the statistics book. Let's do this example using our calculator. About 10% of workers in the United States commute to their jobs by carpooling. You randomly select 8 workers. What is the probability that exactly 4 of them carpool to work? 10%. We interview 8 of them. We want to know the probability that exactly how many? 4 of them go to work that way. So I go second distribution. It's just the same thing I've been doing. Binomial Pdf. I'm going PDF because it's exactly 4, not like at least 4 or at most 4. 8 trials. Probability of success is 0.1. The x value is 4. And boom, over. A lot easier than having to look stuff up in the book. 0.005 basically, or 0.0046. Okay, on to the next page. This is a fairly long section. The next section will not be as long. Okay. Graphing a binomial distribution. About 60% of cancer survivors are ages 65 and over. You randomly select 6 cancer survivors and ask them whether they are 65 years of age and older. Construct a probability distribution for the random variable x, then graph the distribution. So if we interview how many people? 6 people. 6 is the number of trials. It's the n. What's the possibilities for what x can be, which is that many out of n? It could be 0. It could be none of them are over 65. It could be one of them is over 65. It could be 2, 3, 4, 5, or all 6 of them are over 65. So what we would do is we would find the probability for each of those outcomes. All right, and the way that we do that is with the calculator again. I would put in the number of trials would be 6. The probability of success on a trial would be 0.6, and x would be 0. And I would get that answer. And then I'd change x to 1, and I would get that answer. I would change x to 2, and I would get that answer, and so on until I finished all of the possibilities. Then to graph it, you would construct a graph like this with an x and a y axis. Notice that the x-axis is the x value. It's the number of, it's all the possibilities. So in this case, 0, 1, 2, 3, 4, 5, or 6. So just put 0, 1, 2, 3, 4, 5, or 6 on the x-axis here. And notice that the y-axis is the probabilities for those possibilities. So notice that the probabilities here, the highest it gets is 0.311. So they did a pretty smart thing. They counted by basically 5, or they counted by 0.05, 0.05, 0.10, 0.15, 0.20, 0.25, 0.30, 0.35. So that was their top line because it didn't need to go any higher than that. The first one is 0.004. So for 0, it doesn't go very high at all, like not even a fifth of the way to 0.05. The next one, 0.037. 0.037 is just a little bit short of 0.05. The next one, 0.138, would be just a little bit short of 0.15, and so on and so forth until you've got all these bars graphed. And that is the graph of your binomial probability distribution. Notice that this graph, what would you say, where is the mean? The mean is going to be somewhere close to the tallest bar. So probably a little bit less than 4 is the mean. Right? It's right there on the 4 bar, but maybe just a little bit less than that because of the taller bars here. Where is the shortest bars? The shortest bars are over here on the left. Okay? And in fact, you could say there are more bars to the left of the mean than there are to the right. That's called skewed left. It's a skewed left distribution. Wherever the shortest bars are, that's where the skew is. So this is skewed left. In fact, for a binomial distribution, anytime the probability of success is less than 50%, it's going to be skewed left. Anytime the probability of success is greater than 50%, is going to be skewed right. And anytime the probability of success is exactly 50%, it's going to be a perfectly symmetrical distribution where it's the same on the left and the right and not skewed either way. Next page. All right, mean, variance, and standard deviation. We can use the formulas we've already learned for mean, variance, and standard deviation for probability distribution, but the properties of a binomial distribution enable us to use much simpler formulas for a binomial distribution to calculate the mean and standard deviation. The mean of a binomial distribution is very simple. It is simply the number of trials times the probability of success on each trial. So let's take this makes a lot of sense. Let's take my free throw example. If I'm a 60% free throw shooter, and I'm shooting 10 free throws, what is the mean number of free throws? The mean number of free throws that I am going to make. It's going to be n is 10, p is 0.6, 10 times 0.6 is 6. So the mean number of free throws that I would make out of 10 would be 6, and you could call that the expected value. That means if I go in today and shoot 10, if I go in tomorrow and shoot 10, if I go in the next day and shoot 10, then I may make more than 6, I may make less than 6, but I'm going to average out to about 6 out of all those experiments. All right, the variance is just n times p times q, so 10 times 0.6 times 0.4. The standard deviation will be the square root of that, the square root of npq, the square root of 10 times 0.6 times 0.4. Okay, let's use that to do this example. In Pittsburgh, Pennsylvania, about 56% of the days in a year are cloudy. Find the mean variance and standard deviation for the number of cloudy days during the month of June. Interpret the results and determine any unusual values. All right, so first of all, we're going to call success a cloudy day based on the problem. So what's the probability of success? What's the probability of a cloudy day? 0.56. What is the number of trials? Well, it's the number of days in June. How many days are there in June? 30 days has September, April, June, and November. June was in there, right? So June has 30 days. So 30 is the number of trials. All right, so what we would do to calculate the mean would just be to do 30 times 0.56, and that gives me 16.8. So the average number of cloudy days in June would be 16.8. We would, if we had to put an expectation on it, we would say 16.8 days. The variance would just be 30 times 0.56 times 0.44, which is 7.4. The standard deviation is just the square root of that. So take the square root of that and you get 2.7. So on average, there are 16.8 cloudy days during the month of June. The standard deviation is 2.7 days. So if you want to get unusual values, anything that is more than 2 standard deviations away from the mean is unusual. So you would just say 16.8 plus 2.7 plus another 2.7, which gives us 22.2. So anytime you have the month of June with more than 22 cloudy days, that's unusual. You also go the other way. You say 16.8 minus 2.7 minus another 2.7, which is 11.4. So any month of June that would have less than 11 cloudy days would also be unusual. If you wanted to say, quote unquote, very unusual, it would be 3 standard deviations away from the mean. So you just add 2.7 one more time and subtract 2.7 one more time on the low end. And so in this case, you would get 24.9. So if you had more than 25 cloudy days in June, it would be very unusual. Or if you had, let's say, less than 10.4, 9.4, 8.7. So a June with less than 8, with 8 or less cloudy days would also be very unusual. All right, and we're talking about, obviously, just in Pittsburgh, Pennsylvania here. And that is it that's all the examples for section 4.2. Good luck on that assignment, and I'll see you again in 4.3.